Okay, so
start the sharing the screen, maybe.
Yeah, and
Okay.
feel free to do it. Thank you so much. All right, so hello everyone. Welcome to the Informed Data Mining Society webinar series. And today it's our pleasure to invite Professor Xie from Georgia Tech to give a wonderful talk titled Generative Model for Statistical Inference. So give me a few minutes to make an introduction for Professor Xie. Professor Xie is a Coca-Cola Foundation Chair Professor at Georgia Tech in the School of Industrial System Engineering. She's also the Associate Director of a Machine Learning Center. From 2017 until 2023, she was the Harold R. Mary and Nash Early Career Professor. She received her PhD in electrical engineering from Stanford University in 2012 and was a research scientist at Duke University. Her research lies at the intersection of statistical machine learning and optimization in providing theoretical guarantees and develop a computational, efficient, and statistically powerful method for problem motivated by real-world application. She received the National Science Foundation Career Award in 2017 and the Informs Wagner Prize finalist in 2021, and the Informs Garver Early Career Award for Excellence in Operation Research in 2022. She is currently an associate editor for IEEE Transaction on Information Theory, Journal of the American Statistics Association Theory and Method, and also Operation Research Sequential Analysis, Design Method, and Application, Informs Journal on Data Science, and then currently she's an area editor of NIPS, ICML, and ICLR. So, okay. Professor Xie, do you want to start your?
Yeah, absolutely. Okay, thank you so much, Professor Zhou, for giving the very kind introduction and the great opportunity to present research here. So I would like to share our recent line of work along this generative model, how to use generative model for statistical inference. I'll explain what do I mean by inference in this particular context. And I think I have about 50 minutes to present or so. So it's a webinar, so I don't know how to answer your questions, but I guess the host will let me know if there's any question, and so I'll be happy to take questions. So please do feel free to interrupt and ask questions. Okay, so this talk is about generative models. So I'm sure we all have experience with generative model recently, which is one of the hot topics. For example, ChatGPT, right? So if this is becoming a nightmare of many professors, and you could feed a homework question there, and the GPT can come up with a very sophisticated answer to the question. So this is an example of text generation, and even beyond that. There's also the image generation. For example, I can use this to create $1 million pizza fictitious picture that actually looks pretty interesting. And so there are many applications of generative models, all the way from text generation, images, protein networks, and so on. And so today's talk, we want to be able to, answer the question or try to, provide some answer in this direction of saying, what exactly is generative model, and can this be useful for solving some of the foundational methods for machine learning, inference, and so on. So I think largely speaking, generative model aims to learn underlying distribution from observations and also generate new samples following the same distributions. So for example, we have collected a bunch of pictures. These are the pictures of the birds and dogs. And so these are sampled from some true but unknown underlying population distribution, but we would never know this distribution. We can only at most hope to estimate this distribution from these observations, these samples. And so then we can hopefully generate some picture following the same distribution, a new picture of a dog and birds and a frog, hopefully, that we haven't seen before. And so answer this question. And so the center topic for today is, can we learn the data distribution, which is foundational to statistical inference. So once we can learn this distribution, we can use it for many downstream tasks, such as generating samples, answer questions, making predictions, and so on. In traditional statistics, the distribution is typically described by a parametric model. For example, we choose a certain distribution family indexed by a parameter theta, and we can observe the data, and then we hope to estimate this parameter using the data, right? So parametric model has been studied a lot, and there's many beautiful theory around it, but it is believed to be not very efficient sometimes for high dimensional data. In particular, the choice of the model beforehand could lead to model mismatch and so on. The generative model can be viewed as a new way of doing this task, which is an implicit representation of the data distribution using neural networks. In terms of estimation of the density or distribution, which means that if we can evaluate the likelihood, give it a new test sample, we can evaluate what is the chance for this distribution to happen, and also be able to draw new samples, which are synthetic samples that's not in the original data. And hopefully this synthetic data following the same distribution as the data we have collected. So if we can achieve likelihood evaluation and the sampling, and we're happy and say that we have learned a data distribution in this particular context. So this is a more like an implicit way of representing the distribution. So what are some common generative models? And so in I guess machine learning in particular in recent years, this is a very, very popular problem, and it has many applications. And so the approach for generative model typically is to say that, how do we come out with a function mapping f? This f is typically parameterized by some neural networks, such that this f can help us to convert noise into data. For example, my noise is going to be a white Gaussian noise. And so if I can learn this neural network mapping f that remembers the pattern of my data, the distribution of the data, then f of the z, the transformation of my noise, will become a sample out of the data, for example, a picture of the cat. So many generative models are of this particular form. For example, all the way from the earlier generative adversarial neural networks, again, which was popular since 2014. And there's also, the well-known, widely used variational autoencoder, VAE, and more recently, normalizing flow networks and score-based diffusion models are very popular. And so these two approaches are different from the previous approach in the sense that instead of learning one f directly represented by one neural network, these approaches try to learn this f gradually as a continuous process, okay, to gradually convert the noise into data. And the motivation for doing these is normalizing flow and score-based diffusion models typically is to solve the difficulty and training of the generative neural networks. For example, again, if you just want to find one f to convert noise to data, there has been proved to show a lot of difficulties in training and design of the neural networks, such as mode collapsing problems and so on. And so, okay, so given these background information, so today's talk, here's a roadmap. I start with some background information, and then I'll talk about, we propose a new flow generative model, which we call the JKO-iFlow. So it can achieve much more efficient generative model using few iterations and smaller neural networks. And in addition, we can also provide theoretical guarantees. And then I'll also showcase this can be used for solving other problems other than distribution estimation, such as distributional robust optimization, the so-called DRO problems. Okay, here's the setup. So suppose we get some samples from the data that follow, these data follow some unknown distribution P. And so our objective is to learn a invertible map F. And if the data is d-dimensional, little d-dimensional, we hope this map is a mapping from RD to RD, and this map is invertible. And this F is going to help us to convert the noise into the data, and also the F inverse can pull out, the other direction. why do we need invertibility? Is because we want to be able to evaluate the likelihood of the data. Then from probability, we know that if we have the transformation of the random variable x equal to fz, then if you want to evaluate the likelihood of the data x, it is related to the likelihood of z. In this case, the Gaussian, for example, we know what the log pz is going to be. Then as long as we know this log, the determinant of the Jacobian of the F inverse, and then we can basically relate the likelihood of the noise to the likelihood of the corresponding data. And this can help us to evaluate likelihood using the so-called change of variable formula. And so in order to do this, you can see we need to be able to have this F that is invertible, means that you can convert the data to noise, but also noise to data. And also, once we have that, we can evaluate this term in the box to help us to evaluate likelihood. And so, like I said, the difference of this current line of work is different from, again, type of a generative model in the sense that our objective is to say that learning one big F that convert noise into data could be difficult. And so instead, we're gonna divide this task into a sequence of smaller steps, and each one of the smaller steps is going to change the noise a little bit towards the target, towards the data distribution. And so basically this is saying that, for example, you start from some Z, and then this is a sample from the noise, and then you pass this to the F1, the first mapping, and this gives us X1, and pass it to the second mapping, and so on. So after capital N steps, we can, after this, we hope this will converge gradually to the distribution of the data such that this X, right? X is going to be XZ passing through all of this F together, and that's going to be following the distribution of the data. And so this line of work of learning a sequence of mapping, and then the big F is the composition of the sequence of mapping, has been used in earlier approaches in designing normalizing flow, and for example, NIS and IResNet. And so in order to ensure this F and each subsequent little f is invertible, and typically they require special neural network architectures, or they need additional computations such as spectral normalization. And so because of that, requiring special network is not desirable. This can limit the representation power of neural network. So we want that neural network typically have a really good representation power. It is very strong in expressing the reality, approximating to reality. So if you're required to have a special structure, that is not desirable. So to overcome this, another type of approach for this, finding sequence of mapping is through the so-called neural ODE, which was introduced by Chen et al. In 2018, and also the subsequent work FF Jordan. And so instead of finding a sequence of discrete mapping and couple them together, this line of work, the idea is to say that let's, find a, model this whole process as a continuous process. And so suppose we have, starting from time 0, and the data collected at time 0 following some distribution P. And then if we keep moving this data according to the so-called velocity field, which is this little mapping V, which is indexed by T. So this V essentially is telling us, given the current data xt, in which direction and in what magnitude should we move this data? And so that can be interpreted as the velocity. And so if we do it this way, we move the data. By moving the data, this also changes the corresponding underlying distribution. So that's the idea. And so you can see this way of describing is really sort of like a statistical mechanic way of viewing the data as particles. And by changing the particles, we're changing the underlying distribution. And the nice thing about this is if we do it this way, then we don't have the restrictions of the neural network architecture choices. And so this velocity field can be parameterized by free-form neural network. You can choose, it's very general. For example, you can choose, a particular neural network architecture, such as a feed-forward layer or convolutional neural networks, which works great for images, or graph neural networks. If your data really lives on the graph and observations are on the vertices, then we can use graph neural networks. So any of this kind of neural networks can be used to parameterize the V. So that is a nice thing about this. And so using this idea, right, so now we view that converting the data distribution to noise is a whole continuous process. This T is the fictitious notion of the time, right? So if you gradually pushing your data towards the target, which is the noise in this case, and then we can discretize this continuous time notion and implementing each discretizer step as when the digital neural network block inside this rest block, you can use the most suitable neural network to approximate it. So that's the idea. And so you can also ask the question, how do we ensure the invertibility? Remember, we need this in order to evaluate the likelihood. And this actually provide benefit in terms of stable training and basically good, and stable generative model. The invertibility in this context can be ensured by the continuity, basically. So it's very simple. And so given that we have this continuous way of moving the data that induce the underlying distribution change, and then if we discretize it and discretize from time t n-1 to tn, and then the forward mapping is just simply integrating the velocity field in the forward direction that gave us the forward mapping. And then we can invert this by just playing back in time. If you invert the time backwards, and this will give the inverse of this mapping. And so you can see this is really, I think, the essence of neural ODE in the sense that typically, right, it is very difficult to find a neural network that is invertible. But in this particular neural ODE design, the invertibility is ensured by we parameterize the velocity field by neural networks, right? So then the mapping itself actually is through numerical integration of this velocity field, and then integrated forward versus backward will give us the forward mapping and the inward map. So this ensures invertibility. Okay, and so because of that, then we can also evaluate the likelihood, like we said before. We want to be able to talk about the probability of observing a particular sample. And under the neural ODE parameterization, then the likelihood can also be evaluated using a so-called instantaneous change of variable formula. And as the particular expression, you can see this time is computed in terms of the velocity field. And essentially it's given by this divergence, right? So so-called divergence applied on the velocity field, this mapping of how to move the data points in certain direction and so on. So you can compute this numerically by Hutchinson approximation, which is kind of standard in numerical computation. Okay, so this basically give us a picture how to do this, and to keep in mind, actually, in both cases that computation have to require us to compute the Jacobian and high dimensions, but there are numerical techniques developed to handle this, so it has been done in practice. Okay, so far I have talked about this normalizing flow type of approach. And so you may have also heard about another type of generative model, which is called diffusion models, which has achieved really good performance in image generation and so on. So how is this compared to the flow model that I have just presented? And these are two different types of generative models that are popular, both continuous time. And so the diffusion models is based on a different kind of statistical mechanics philosophy, which is to say that let's try to simulate a stochastic process by adding noise. And then I can gradually convert the image of the dog into the, some noise, for example. And so, but there's something called a score matching. Basically, you say that if I record the process of converting a dog into noise, and if I replay and reverse time to go from the noise to the data domain, and then I can also have the corresponding reverse time diffusion process. And then if I know the score function, which is the gradient of the log function of the data, so that then I can also invert the noise into my image. So that's based on some known results in diffusion, process. And so you can see the difference from what I had before is in the normalizing flow, we directly apply some velocity field on the data, right? So there's never a noise being injected here, versus this diffusion model is following a stochastic process, which you have to add noise to implement this. And the typically diffusion process is based on the SDE, and in particular OU, or this Ornstein-Uhlenbeck process. And so you can see this is described by this diffusion stochastic process, which describes that you have to move your data according to some so-called drift, right? So minus the gradient of the v of dt, this is the drift, the trend. And then you also have this blue term, which is additional noise you have to inject in the process. And this noise is typically a Brownian motion, or basically like adding white noise to it in order to achieve this goal. And you use a reverse time diffusion process to sample. And so you have to do square matching in order to be able to invert in time. And so this type of model is typically designed as a sampler. And so I would say the previous normalizing flow model that I had presented, I showed the benefit that you can directly compute the likelihood function, right? So using the change of variable formula. And in this diffusion model setting, you simulate the stochastic process, and so you can get a sample out of it by simulating the stochastic process. But it is indirect. You can still obtain the likelihood, but there's no direct way for doing that. So it's more like a sampler kind of approach. So in order to evaluate likelihood, we tend to use normalizing flow. So in today's talk, I'm going to focus on talking about the normalizing flow. Okay, so great. So we have normalizing flow as a way to learn the density and evaluate likelihood. And so is it good enough for us to apply already? And so it has also facing some challenges. One of the challenges is you can see that the idea in theory is to say that we want to be able to represent the movement, the conversion, or the change of the distribution from the data to noise in a continuous fashion, and then be able to invert as well. And then you discretize time. But in order to implement it, we have to discretize the time, and each discretization is giving us a neural network block. And so in order to have a good precision, we have to discretize into many, many steps. And this will lead into many blocks of neural networks, right? So you end up having a very gigantic neural networks with millions of parameters, and you have to tune these neural networks at the same time in order to achieve the goal of matching the data to the noise. And so because of that, it tends to be very, it's more difficult to train basically. And existing result also didn't say how good, of this approach in terms of learning the distribution. So I guess in statistical inference, a lot of times we hope to have some theoretical guarantee to say that we're able to, approximate the data distribution with certain accuracy. So we hope to achieve that as well. Okay, and so like I said, the normalizing flow, and actually both normalizing flow and the diffusion model that I just talked about before is also based on discretizing the time but adding noise. And they, in order to implement and in practice, we have to discretize the time, and then there are many, many small steps, right? So, and then you end up having a very large neural networks, and then you can hope to achieve the goal by, large number of steps or neural network blocks. And so because of that, these models tend to be slow. Okay, so this has also been pointed out by other people's work. For example, this one, some 2021, that generative model tend to be slow. Okay, so theoretically, this looks all nice and beautiful and has a potential for learning the distributions. And so now, can we fulfill this promise, like promise the better guarantees and answering these challenges? And so such that we can still compute the likelihood, but at the same time, can we make this faster? Can we speed up the process and using as few blocks as possible to achieve the goal? And so also provide some guarantees in terms of how good the generative model it is, and such that it can be close to the true distribution. Okay, so hopefully this gives enough motivation. What we're trying to do here is to develop a better, faster generative model based on normalizing flow, and can have really good performance, also have some guarantees, and it's faster in the sense we can use as few steps as possible. Okay, so now I'll explain this work. So this is based on this paper that is recently appeared in Europe's 2023 as a spotlight paper. And so the so-called JKO-iFlow, and so as a reminder, we aim to learn probability distribution for high-dimensional data represented by neural networks. And so we hope to find likelihood. And so remember, there's a change of variable formula. So we can, as long as we stay within the normalizing flow framework, we can still evaluate the likelihood. And so we hope to have a stable and faster training, and then also have some guarantee. In particular, Later, in the later of the talk, I will explain what exactly we say in the theory part. But basically, this approach can speed up the process and using as few steps as possible, and then we can have actually exponentially fast convergence towards the desired distribution. So this is pretty good. Okay, so as a recap, the objective is to say we want to be able to find a mapping, and that is parameterized by this V, the velocity field, and then underlying that, you have the neural networks. And so we want to be able to find this mapping to continuously map data to noise and also be able to go back. And how do we do this in a faster way? So this is inspired by well-known scheme called the JKO, which is developed by 3 authors, Jordan-Kinderleherer-Otto, in a classic paper in 1998 in the numerical partial differential equation literature. The idea is basically saying that we try to, finding the fastest way of moving my data from the data distribution to noise following some gradient descent. Okay, but this gradient descent is not in the vector space because we are moving in the distribution space. So we have to find a certain way of moving the data such that the distribution is moving in the gradient of my objective function in the Wasserstein metric. And so in implementing the actual algorithm, we're also going to build this on top of the neural ODE approach. So that gives us a good algorithm. And so basically what that means is we're going to try to find the optimal velocity field that will move our data distribution to noise as quickly as possible. Okay. All right, so since we're going to talk about the probability space, and so let's try to think a little deeper, right? So if you want to do gradient descent and moving the data distribution to noise in a fastest fashion, okay? And so we're moving in the probability distribution space. What does the space look like? Okay, so can we add 2 probability distributions? So in vector space, we can add. But if you simply add a 2 distribution, it is not a distribution, right? Because the distribution needs to normalize to 1. So this is something special about the space of distributions. And so, for example, okay, if I cannot directly add them, I can probably add a weighted version, for example, 0.4 of P1 plus 0.6 of P2. And this gives us a distribution, it normalized to 1. However, this kind of weighted combination sometimes is not interesting enough. For example, if my P1 is a distribution of the picture of the birds, P2 is a distribution of the picture of the dogs, and I simply perform a weighted combination of the 2, I end up having a mixture of the Gaussian distribution with 2 modes. And so I cannot really use this to represent a distribution of a frog, right? So because it's not a mixture of these 2. And so instead of having a weighted combination of the distributions, it's more interesting to consider the underlying geometry and perform a geometric interpolation between distribution P and Q. And for example, this is an example actually achieved by our algorithm, right? On the left-hand side is the distribution of the dog. But as you can see, if I gradually convert my data, and then on the right-hand side is a distribution of the frog. You can see there's something in between, right? The dog and the frog. And so there's some interpolation between the 2. So you can see this is not a simple weighted average of the 2 distribution, but it is more like a continuous interpolation between the 2 distribution. I gradually convert that. So this kind of geometric interpolation is called a geodesic, right? So distribution lives on this geodesic space that normalized to 1. And this is the kind of space we're going to consider. Okay, so, and because of that, right, essentially remember that we want to be able to find the velocity field, which is, for each data point x at time t, this velocity field tells us in which direction, what magnitude should we push this data point. And so in terms of this picture on the left-hand side, and this is in the data domain, right? We'd say that if you have these observations, which are these dots, and then we want to be able to find this velocity field, which are represented by these arrows, and it tells us, how do we push this data? As you're pushing these dots, which are the data observations, right? And then if this underlying contour is this unknown distribution that they sampled from, but if you can push the data points in some fashion and this also changed the underlying distribution these data are sampled from, right? So then we can convert the P into some distribution Q. On the right-hand side is my target distribution, which is my noise. And if I can do this in a continuous fashion, right? And then I have this nice invertibility, like I said. So the left-hand side is in the data or the particle space. And so if I have a velocity field, which is this V, right, represented by these arrows that tells me how to move my data, at the right-hand side, like I said, this also induced a change of the corresponding distribution that the data samples from. And so how the distribution evolves, it's following a so-called continuity or Louvel equation. And so you can see it's described by a partial differential equation. And so xt is the data at time little t, and if their distribution is according to some rho t, and then the rho t needs to satisfy this equation, the partial t of rho t plus the divergence of the partial t of the vt. You can see the vt is the velocity field, right? So if you choose the velocity field in a different way, then your distribution is going to move in a different way. And so I have to satisfy this equation equal to 0. And you could ask, why do I have this equation? And so this essentially is because your distribution rho t is a distribution, so it has normalized to 1, right? So you have to say integral of my rho t equals to 1, right? So that's the legitimate definition of the distribution. So my distribution had to follow this continuity equation. Okay, so this is the basis of everything, basically to say that now if I want to be able to find a way to push my data to Q, and I need to find a corresponding V that will achieve this goal. Okay, so here's my animation. I want to show, how this is being done in the algorithm. And so this example shows that you can see on the left-hand side, right, I have the distribution of arrows, and which is a two-dimensional distribution with a fairly complicated support. And so my mapping is gradually pushing each of those dots on these rows, right? Each dot is one data point. And so the forward direction is converting the rows into the noise. And the backward direction is, you can see it's also invertible. It can pull the noise back into the rows domain. So once I have this mapping in both directions, that's great. I can evaluate likelihood of the data. I can also take a fresh sample, a new sample in the noise domain and map it back. That gives me a sample following the data distribution, right? And so basically on the bottom, that showcase, right? So I have this process. All I need to figure out is how do I push my data in some direction with some magnitude, and then I can change the underlying distribution. And so as you can imagine from this, great, I have to figure out how do I represent change in the data domain will induce the change in the distribution domain. My goal is to figure out a way to push my data distribution to noise and also be able to go back. And so I need to follow this continuity equation. But as you can imagine, the choice of the velocity, how I push my data is not unique. And so this example shows, this is the case on the top, right? So you can see there is a faster and, a shorter distance way of pushing data distribution to noise. And on the bottom is another way of pushing the distribution to noise and backwards, but it takes longer trajectory, right? Because and so essentially this showcases the difference, right? So there is a faster way. If I still follow the continuity equation, but there is a faster way to find this mapping to push the data to noise and backwards. How do I find this faster way? And this is really the key of designing a faster generative model and actually also more stable to train, is we need to be able to find this faster and shorter paths to move the data to noise distribution, and to following the top panel, this is, shorter paths and the straighter trajectory. And so to achieve this, essentially we need to, perform some regularization. So essentially what happens is we need to find the shortest path to convert the distribution, okay? And so how do we find the shortest path? Number one, first we have to introduce the notion of how do we measure distance in a probability space? And so we're going to consider the so-called Wasserstein metric, which is a popular choice recently in machine learning. So this measures the distance between probability distributions. And so there are many choices of measuring the distance. For example, the KL kind of likelihood divergence is also type, but this basically is, measuring the distance between distribution as the minimum cost of transporting probabilities, right? So, for example, the so-called Wasserstein 2 metric, and this picture showcases this idea. You have one distribution P, another distribution Q, and if I can move the masses around, and then there are some costs of moving my masses, and the cost is going to be the L2 distance of moving this mass. And so if I can find out, the smallest cost way of converting P into Q, and that gives me the so-called Wasserstein 2 metric. It's also called the Earth's mover distance, as you can imagine. It's describing this kind of property, right? And so the Wasserstein 2 metric have the so-called Cantor-Wedge formulation. And so essentially you want to be able to find coupling. And there is actually an equivalent formulation called the Munch. It actually arises from earlier contexts, but later on people realize there's some correspondence between the two. And the Munch is to find a transport map of mapping the distribution from P to Q, and then finding the transport map that will minimizes the cost essentially. And so, as you can imagine, right? Now my problem becomes like finding what is the
Looks like Dr. Shi lost connectivity. Yeah, just hold tight and see. But yeah, we can see where she is.
Sorry, everyone. Professor Sher just texted me a message that she has a power outage in her place. So I'm not sure she's able to get back to connected soon. So let's wait for a couple minutes and see how it goes. Thanks. Yeah, so Professor Sher will come back soon. So thanks for your patience.
Oh, hi everyone. I'm here. Sorry,
Yes,
I just had a power outage. Oh my gosh. So I'm presenting from home. So let me try to use my phone. I think I should be able to do it here. Give me 1 minute. Thanks. And sorry everyone for the inconvenience.
sure, no problem.
Yeah, 1 minute. Yeah, but I hope everybody is still with me.
Yeah,
Sorry.
everyone's still here. No worries.
Yeah, I apologize. Yeah.
No problem at all.
Yeah. That's why I actually also work on power outage data where I collaborate with Oregon National Lab. And so actually one of the applications of the generative models that I presented here is to adopt this to generate adversarial scenarios, and such as in power systems, right? So what are some possible bad scenarios that we can throw at the power system? Okay, so actually, you can hear me, right?
Yes, we can.
Let me share the screen. Okay, so 1 minute. So I think I should be able to do it. Share screen. Start broadcasting. Can you see my screen?
It's coming.
Okay, great. So yeah, and so where we are. So I'll capture the high level idea. I think there's a lot of details, but I think I hope you guys are still with me. So what I'm trying to say is that we want to be able to find a faster way of moving my data to the noise and also be able to go back. And so in order to do this efficiently, I have to do this in the shortest distance measure. And then how do I measure the distance? I have talked about using Wasserstein metric. And so I'm introduced this main result, which is the so-called JKO scheme. And so basically, I'll skip that. And this coming from this classic paper in numerical PDE. And so this is the basic idea. We basically want to say, remember our objective is to move the distribution towards a Gaussian. And we want to be able to move this towards Gaussian in the sense that we want to minimize the KL, which is a Kalbach-Leibler divergence between my rho and the next distribution, and the Q is my Gaussian in this case. And so I want to solve the problem of minimizing the rho and the Q. But at the same time, I want to do this in many steps. And in each step, I basically want to say I want to move closer to my Q, but at the same time, not getting too far away from the previous distribution. So I have this regularization term, which is 1/2 gamma. This 1/2 gamma is the magnitude of the regularizer. And this green term is the Wasserstein 2 that measures how close, how far away is my next step from the previous PN. So, and if you look at this, essentially, this is pretty much like trust the region or proximal kind of algorithm. You see that I want getting closer to my Q, the Gaussian distribution, but at the same time, I don't want to move too far away from the previous step. And so, so where does this come from? Actually, there's also some connection to dynamic formula of the Wasserstein. I will skip this. And I basically want to say that taking that idea, now we can develop this faster, quote unquote, fastest way of moving closer to my noise. And that gives me a faster convergence of the generative model through this JKO idea. And so I parameterize my distribution using the Wasserstein push forward operator math. So there's a lot of notations, but basically all you need to remember is that my Q is my target distribution, in this case, the Gaussian, and my rho is where do I want to go next. So this T sharp is basically, T is related to how I move my data through the velocity field. And so T sharp is basically, if you move the data, you're going to move the distribution, right? So this T sharp is actually basically saying, if I choose a certain velocity field, that induces a corresponding T that's going to move my distribution from the previous step Pn to the next step rho. Okay, and so I want to be able to parameterize my T using velocity field, and then just following my neural DE and so on. Okay, so I know there's just a lot of stuff, but I think the next example is going to illustrating exactly what's happening here. So I'm going to give a simple example. Okay, so the nice thing about this is actually you can see I decouple the problem of designing a big mapping to interpolate the data to the noise into this, this so-called progressive training. So this time I don't have to tune all the blocks at the same time. I can just choose what is the best block for the next one and fix all the previous ones. So this is much easier to train and give us more stable training. Okay, now let's illustrating what exactly is the algorithm doing. So in the sample version, I can write down the KL divergence and enclose some expression, and also the Wasserstein 2 regularization that tells me I'm not moving too far away from the previous step is actually very, very simple. You just look at how much has been moved by this velocity field. And so the difference is you can see this number resample inject the noise. And so this is my example that I want to illustrate. Suppose I only have 3 data points at time t0 and a following distribution p0. And so I'm trying to find what is the best velocity field to move my data that induces my underlying distribution change to getting closer to a Gaussian. In order to do this, following the previous prescription, I need to solve this optimization problem for my velocity field in this short time interval, like this t is between t0 and t1, which is a short discrete time interval. And so, and this will move my data to the next step. Okay, I do this one step at a time, right? And the next step, I find what my velocity field needs to be in the next time interval. And this time my objective function will only take the current data point. And the first term is minimizing the KL, getting close to the Gaussian. And the second term is measuring that I'm not moving too far away. Okay, so you can keep doing this recursively until we have a large enough n, this capital N, each of this movement is one neural network block, and essentially solving this optimization problem is tuning neural networks. And so after a big N number of steps, we can hopefully achieve our goal, getting close to the distribution. And so that's basically illustrating the idea, right? So basically, like I said, the difference of this normalizing flow approach from the diffusion model is you can see this is particle based, means that we're just looking at how do we push the data, and that induces the change in the NRI distribution. And compared to the diffusion model tried to sample from the noisy trajectory. And because of that, you actually have to inject a lot of noise in the process. And so that is not ideal, right? Because injecting this noise is artificial. That's only a way to simulate the SDE. And so, in fact, if you ask what is the magic here, why you don't have to inject noise, that is because actually mathematically, the SDE-based approach induces the same distributional change as the continuity equation if you set the velocity field to be proportional to the score function. So essentially, this is, ours is also following the same kind of math, but the difference is we don't learn the score matching directly. And the nice thing is, if you do this in the particle space, you don't have to inject the noise. You don't have to inject noise artificially, which actually will make the performance worse. And so we're not the only group that observed this. And so this is actually a picture from another group that also have this point that it is better to do this in the particle space, meaning that you have 100 data points, you just figure out how to push these data points to move the distribution from your data to some noise, for example, in the target. In this case, is to move to a checkboard. And on the right-hand side, this is SDE approach, right? You're hoping that you have some diffusion process with a lot of noise. And so statistically, on average, you're getting some distribution, but you have to have a lot of particles and you diffuse. And so you hope that on average, this is achieving the goal. So it's a lot slower. And on the left-hand side, our approach is a lot faster. And so indeed, numerically, this is the case. So this is the example of the rows I showed earlier. The first panel A is the true distribution. So, and the second panel is our approach. So basically, we verify that if you move your distribution from the rows to the noise, and then you also go back, if you have a pretty nice and precise numerical, result, then we should be able to recover the rows pretty accurately, right? So indeed, you can see that in our JKO-iFlow, the distribution is very much close to the true distribution, versus the last panel is this score matching as score SDE. You can see it's very noisy, right? Still have some shape of the noise of the rows, but it has a lot of noise that buries the nodes, and that is because there's a lot of artificial noise injected in the process and go back. And we're also doing better than the other flow-based methods because of the regularization we introduced by the Wasserstein, that we're following the shortest trajectory on the probability space. And so, yeah, we evaluated this on actually different, other data. Sorry, by the way, can you still hear me?
Yes.
Okay, great. Yeah, so because we're having another power outage episode. It's quite eventful today. I'm glad I'm using my phone. Yeah, so we're able to achieve faster convergence compared to the state of art. We compare with many score-based matching and other type of SDEs and approaches, but we are achieve the best. And also very accurately estimate, more accurate estimation of the likelihood function in terms of the density estimation. So there we have both better density estimation and the faster algorithm. And so usually the holy grail test for this is to generate images. So this is one example showcase these images generated using our models. On the top is the generated MNIST digits, and the bottom is the generated the CFAR10 and ImageNet 32 images. And so all of this actually is generated. They don't exist in the original training data, but as you can see, I think they're pretty, realistic. I would be surprised to see they're quite realistic, and you can measure in terms of the performance metric. The FID score is also kind of quite competitive. And so, okay, I think how much more time do we have? Maybe 5 minutes.
Yep.
Okay, great. So yeah, okay. So thanks everyone for sticking around. I mean, seems to be a lot of technical challenges today. So with the remaining 5 minutes, I would just like to highlight a few related directions. So I propose this new method, JKO-iFlow. If I would say the main ingredient is number one, it is following this normalizing flow approach, which you don't have to inject noise. And the new ingredient is we made the connection to optimization. So you're following the shortest trajectory to learn the mapping, and then the shortest distance is measured by Wasserstein distance. And so those are new contributions. And so we're also able to prove the theoretical guarantee of the generation in the sense that we could say if the true distribution is P, and then through this approach, we find an estimated distribution P hat, then we can guarantee that the total variation distance between P, the true distribution, and the P hat, the learned distribution, is going to be small, so it's very close to the true distribution. This area is controlled by epsilon. Then we can do this using the order of the log of 1 over epsilon steps. And so this is so-called exponential convergence, right? You use exponentially log of 1 over epsilon number of steps to achieve this accuracy, which is quite good, considered to be fast. So this kind of convergence result is obtained by making a connection of this design to basically proximal gradient descent in probability space. And so if you could remember that this each step of this scheme is to solve a small step, and that corresponded to a block of neural networks, and that is minimizing the divergence, in this case KL divergence, this G roll. And at the same time, you're saying that don't getting too far away from the previous step, so we have this Wasserstein 2 regularization. So we're solving this, and if you recognize this, actually in the vector space is known as the proximal gradient descent, right? So here, this is actually proximal gradient descent in probability space. And so because of this connection, we're able to generalize the proof in the vector space to the probability space by generalizing the notion of convexity to the generalized geodesic convexity. So as you can imagine, the reason why we need to do this is because we're interested in optimization in probability space. It's infinite dimensional and it's like living on a manifold. So we generalize that convexity notion. But otherwise, I think it's very much similar to what you would do in the vector space in terms of proving the convergence. And so that gives us the so-called forward convergence, but we also want to be able to say, how do you ensure the invertibility part of it? So you have the generation. And so the main ingredient is there's something called the bidirectional data processing equality. And so basically saying if your mapping is invertible, and then you can preserve the K out, and that actually gives us the final results. Okay, so I know I'm running out of time, but I just want to mention that using this idea, essentially, this gives us a pretty good representation of the distribution and continuous distribution, which is infinite dimensional, right? This is quite non-trivial. We haven't made any parametric assumption, right? It's basically saying you convert the noise into a target distribution. That's it. So this actually can also be used to represent other distribution in other contexts. For example, in solving the worst case distribution in distribution robust optimization. So I, experiencing power outage now, and this has to do with power system resiliency, right? So can we find out a worst case, for example, attack or situation to the power system, and then generate sample from it? So actually the power engineers can design to guard against those worst case scenarios. And so essentially this is known as the, distributional robust optimization problem. So you want to be able to say, let's find a distribution to maximize the expected loss. And this worst case distribution Q is close to my observed distribution P in some metric, and particular Wasserstein metric, and with some radius R that controls how much outrageousness you want to have. And so finding this Q is known to be a difficult problem, but essentially, I think I'm going to skip a few slides just to show you that we can make the connection of this Wasserstein DRO problem with our problem. And so if you introducing a Lagrangian multiplier, and then essentially this problem becomes solving some general loss function, V, not necessarily the K-out divergence, it could be classification error or some other loss. And at the same time, you want to say, I want to find my distribution not too far away, my Q not too far away from the P. And so essentially, the solution we have is just taking the generative model we had before, and then on top of that, learn a further worsening transform mapping. This worsening mapping will make the data distribution to actually maximize the loss, right? So for example, make the classification error larger and so on. So and so this mapping can also be similarly parameterized by neural ODE and other approaches. So here's some examples, right? So what are some worsening samples for classifier is, for example, a dog converted to a frog. And the mapping is also continuous, and the left-hand side actually shows how this mapping is continuous. As you can see, it's based on actually this mapping is learned, and I didn't prescribe anything, but you can see it moved the pixels and colors a little bit, and indeed this converted dog to be almost like a frog, and so on. And automobile becomes a truck, horse become a bird. And so this is useful for adversarial training to robustify the algorithm. And we also use it for data-driven differential privacy to better protect the privacy. And we can also generate this, so far I talk about one target distribution. It doesn't need to be a Gaussian, it can be other things, for example, Gaussian mixture. And we have uses for, we have generalizes for, mapping to data to Gaussian mixture. And it doesn't need to be a Gaussian, or a Gaussian mixture. It can be arbitrary general distribution. So we have generalizes in this particular paper here, and interpolation between the distributions. This can also be used for density ratio estimation. And so we all know that density ratio is quite important for many statistical inference tasks, such as classification or hypothesis testing, right? So we can use this approach for doing that. Okay, so I guess I am done. So I have basically explained this flow-based model, and I view this as a new way of learning distribution in the high dimensions, and by finding a mapping to map the noise to data and also be able to go back. So it's invertible. And so developing faster and stable flow-based model to avoid noise injection is the objective here. And we also proved some guarantees by looking at intersection of this problem with optimization. So this really lies at the intersection of these many things. And there are many potential applications. I listed some of them here. Okay, so with that, I'd like to conclude my presentation, and thanks for your attention and support through this interesting eventful process. Thank you all.
Awesome. Thank you very much, Yao, for your talk. It was very inspiring, very interesting. And
thank you.
Yeah, we have one question from the audience. So first question is regarding the geodesic. So for many well-studied metric spaces, geodesics were proven to be unique for example, in Wasserstein space, Hilbert space, symmetric, positive, definite metric space, etc. So embedding with different metrics lead to different velocity fields, so such as a tangent bundle. And so is there any way to find the best possible metric space on top of which the velocity field can be defined and yields the fastest convergence of density estimation?
Great question. Yeah, thank you. So I guess, sorry, let me go back a few slides. So actually, when we talk about the, this is the vast distribution. So I said about, this one. So the top one is what we did, right? So we introduced this vast metric to find the shortest, kind of like it's piecewise shortest, right? Because each step is solving what is the shortest and next. So it's not the direct geodesic between Q and P. So the bottom one is the old normalizing flow, which doesn't have this shortest path. And so you're right. I think in terms of the definition of the geodesic, right? So in our case, we look at the Wasserstein too, and so in our experiment, actually, when we tried this on the image data, so let me show this example. We actually did an additional step, which is we mapped the data to a latent space. I think this might be what you're asking, that the image initially are pixels, right? But these images tend to lie on the low dimensional manifold, and the intrinsic dimension could be much, much lower than the actual dimension of your image. And so typically people learn this low dimensional representation through some, for example, autoencoder. This is pre-trained, and just map your data into that. And so essentially what we did here is we learned the piecewise geodesic on this latent space, right? So this particular latent space is defined by another neural network, which is the VAE, for example, or other types of latent space learning. And so we don't know how to ensure optimality there, but this did help with the performance. I think it's better than directly operate on the image space. And so which one is the best? I think it's a theoretical question, I guess. I don't have the answer, but I just say that empirically, indeed, we this mapping works pretty well of finding the piecewise geodesic in the latent space, learned by some representation. Okay.
Awesome. Any other
Sure.
questions? Any other open questions? Anything quick? Okay, great. Yeah, I guess it's around 3:30. So even with the technical difficulties, it looks like it worked out. Yeah, and on time. Yeah, I think thank you very much, Yao, for the insightful talk. It was really interesting. Yeah, always great to attend your webinars. I think you have a lot of great insights into the field, and thanks for the quick moving and the flexibility. Very impressive. Switching to your phone.
Yeah, no problem. Thank you. Yeah, sorry guys for bearing with me, and I hope you get something out of it. All right, I couldn't turn on my video, but yeah, this is on my phone. But thanks a lot for everything.
All right, awesome. Well, thank you very much, everybody. Hope you have a good day.
Thanks everyone. Bye.